Hey everybody, it's Rod with the PhotoFair coming back at you with another video. So today I want to talk about telescopes. Yeah, telescopes like this Celestron 4-inch refractor right here. Data shows that about half of all telescopes sold these days are going to be used for astrophotography. So the art of photography and the science of astronomy have kind of gotten closer together than maybe they've ever been before. And that's kind of exciting. And so in today's video, I want to kind of go over some of the differences in the use of terminology and the marketing of telescopes versus camera lenses, because it's very different. Camera lenses, we typically look at a lens based on its focal length and its f-stop. So we're not really concerned with how many millimeters of aperture it has. It's the f ratio. So if we're looking for a 135 millimeter lens, for example, we're looking at, say, a 135 f2.8 or perhaps a 135 f2. Those would be two very common f values for a 135, the f2 being a more expensive lens. I also want to remind everybody before we get into the video, there is a small PhotoFair show at Seawood Photo on June 24th. That's in San Rafael, California. It's in the parking lot, so it's an outdoor event. It's our only outdoor event of the year. It has been extremely well received by the community. This is a smaller event with roughly 25 tables or so. And of course, Seawood will have all kinds of great deals, and we may even have like a factory demo or two as we get a little closer to the event. We'll post information on PhotoFair.com. So be sure to check the website regularly. That's PhotoFair.com. June 24th. We'll have our Portland show at the end of September on the 30th in Portland, and then another show to finish the year at the Newark Pavilion in Newark, California. So again, photofair.com for all of that information. So I want to talk a little bit about telescopes today, because telescopes are a little different than camera lenses. We look at telescopes a little differently, how they're described, how they're advertised, and there's a variety of reasons for that. But the primary difference is the focal length is not the driving factor in a telescope. The driving factor is the aperture. And we're not talking about the f ratio, because a lot of times in photography we think of aperture as being f-stop, which is really not true, actually. The f-stop is simply a ratio of how wide the opening is for the lens relative to what the focal length is. And telescopes use f value, but they don't measure focal length in their advertising. They don't say, hey, you want to get a 1,000 millimeter f10 telescope? No, it would be a 4-inch f10 telescope. That would be how it is sold. And there's a lot of reasons for that. It has a little bit of effect on astrophotography, but more so on observational use. So for example, this is a 1,000, you can't even see this, I can't even get it in the frame, a 1,000 millimeter f9.8 telescope. It's actually a 4-inch refractor. So it has 102 millimeters of aperture. Now, these telescopes, typically you don't close them down like you do a lens in photography. Typically you want to use your scope wide open. You're trying to gather as much light as possible. However, there are times when closing it down would be nice. Typically what they'll do with a telescope is they'll have a hole in the front of the lens cap, and then you can stop it down that way. And that would be for use with really bright objects. So basically there's three types of common telescopes. There's the refractor, which is the closest thing to a traditional photography lens. There is the Newtonian reflector, one of the oldest designs. This is just a giant mirror that gathers light and refocuses it to a secondary mirror and into your eye through an eyepiece. And then lastly is a modernized version of the reflecting telescope, a catadioptric design, either a Schmidt-Cassegrain or a Maksutov-Cassegrain. These are similar to reflector lenses or reflex lenses in photography, which I've done a number of videos on various reflex lenses. So those are the basic types. Each of the three basic telescope designs have advantages and disadvantages. The refracting telescope tends to be the sharpest in terms of images. They're very bright. There's no obstruction in the light path. They do, however, suffer from chromatic aberration. Most telescopes, even inexpensive ones, are at least achromats, which corrects some of that chromatic aberration. And then, of course, the real expensive ones are called apochromatic, and they nearly eliminate chromatic aberration, but not entirely in most cases. Reflecting telescopes have the advantage of being available in very large apertures. 12 inches, 16 inches, even 24 inches are attainable for prices that ordinary humans can afford. That's really their big advantage. The disadvantage, there is a central obstruction in the form of that secondary mirror that blocks a portion of the light. The larger the aperture in that telescope, the less the central obstruction affects the actual light path. The other disadvantage to these are they can get really big when you get the larger ones, and heavy, and may even require some assembly on site. Another optical disadvantage is that you find yourself with something called coma. This is where you have sort of stretched kidney bean shaped stars out towards the edges. This is particularly egregious on fast scopes like an f4, f5, and to a lesser degree f6. Longer Newtonian reflectors, f8 and higher, the coma is not nearly as bad. Finally, the catadioptric designs. I won't go into the differences between the Schmitts and the Maxitovs, but basically these types of scopes are much more compact. They do multiple reflections inside the tube to shorten the overall length of the telescope. These often have corrector glass as well to correct things like coma and kind of flatten the field. They do tend to be very expensive. Not as expensive as apochromatic refractors, but close. So aperture is king. The more aperture a telescope has, the more resolution it can deliver. And so if you want to do high magnification work, you need a lot of aperture to support that. Focal length also affects your magnification. Obviously, with cameras, the longer the focal length, the more magnification you receive. In telescopes, however, because we can swap out eyepieces for viewing, we can get a lot of magnification out of a shorter focal length telescope. The advantage to the longer focal length is that you can use larger and easier to view through eyepieces and still get good magnification. The advantage to the shorter focal length is you can get wider fields of view. For people not familiar with astronomy, there are objects in the sky that are very faint, but they're large as 5 or 6 full moons across. So beautiful giant things like the Andromeda Galaxy. If you have too much magnification, you wouldn't be able to get all of the Andromeda Galaxy into one single view. And so when you go out to dark skies, you can see Andromeda easily with the naked eye, and it is enormous. Makes the full moon look tiny. So this is where a shorter focal length in a telescope can yield better results. For viewing planets like Mars, Jupiter, and Saturn, the longer focal length scope definitely has an advantage. So determining how much magnification you're getting with a telescope and its eyepiece, it's a simple equation. The focal length of the telescope divided by the focal length of the eyepiece. So in this case, longer focal lengths on the telescope will yield higher magnification with the same eyepiece. But in the case of the eyepiece, a shorter focal length eyepiece will deliver higher magnification. So that's here's a chart up here showing you some basic magnifications with various telescopes. So when comparing magnification through a telescope with your camera versus with eyepieces, using a 50mm eyepiece will give approximately the same image magnification as you mounting your full frame camera behind the telescope. However, the field of view through the camera will be more like the field of view with a 36 or 37mm eyepiece. I'm not 100% sure why that is, but my astronomy software says it's so. So for imaging, it's you can make great images through any of the 3 basic types of telescopes. I feel like if imaging is the primary thing, the Cassegrain designs have the advantage of not just being compact, but having the focusing tube in the back of the scope, so the camera mounts right behind the telescope, just as if it were a regular camera lens. Now that would be the case with a refractor as well. Refractors of any substantial size and aperture, however, are very expensive. So your wallet will be on fire for months on end if you want to get a really good refractor. That's kind of the real Achilles heel to refractors. And finally, imaging. 2 basic ways to image with a telescope. One of them is kind of the old-fashioned way that dates back to when all we had was film. This is where you basically, for faint objects like the Orion Nebula or Andromeda Galaxy, or even fainter objects than that, you would do a long time exposure, not measured in seconds, but minutes, even hours sometimes. This required extremely precise polar alignment of the scope and an extremely high quality tracking mount. The modern way is with digital cameras, allows you to stack images using photo software. So this modern system works by, first you take a bunch of images in complete darkness, caps on, everything like that, and a real fast shutter speed. You're trying, and you take a bunch of these, maybe 10, 15, 20 of these. It doesn't take very long. And what you're doing there is you're picking up just the native ambient noise that your sensor produces. The next thing that's done is out at the site in the conditions that you're going to be shooting in, you do basically the same thing, except this time you're using similar shutter speeds to what you're going to be using for the actual photos. And again, you just have the cap on your scope. So now you're getting any additional noise introduced by the slightly longer exposure and the ambient temperature and all that stuff. These are called flats and darks. Then what you do is you take your actual images, they call these lights, and you're going to take a whole bunch of these images at very manageable shutter speeds, maybe a 30th of a second, 15th, 10th, maybe even as long as a second, but you're taking dozens and dozens or even hundreds of images. And then you're done, and you go back and you use software, and that software will actually analyze those flats and darks to determine your ambient level of noise so that it can eliminate that noise. Then it will stack all those pictures, dozens and dozens of images, maybe even hundreds of images, and it stacks them all together to form sort of a super image with all of that detail that was captured over the same amount of time, perhaps as a longer time exposure, but in easy to obtain images. You don't have to have awesome tracking for this. In fact, if you're shooting fast enough speeds, you don't need tracking at all. So then the software produces this image, and you take it into Photoshop and you start working, they call stretching the image. There is a little bit of time involved in this, but I've done this and had some great success on brighter celestial objects like the Orion Nebula. But I've been able to pull out some pretty impressive details, even in my terrible city skies where I live. And I've seen results from folks on cloudy nights that are just amazing when they go out to dark skies and do this. So anyway, that's really nice. It makes it easier to do imaging with digital cameras. So there you have it, a little bit of information about telescopes. That was definitely the 101 version, and I hope you found that useful. Again, don't forget our next PhotoFair show, June 24th at Seawood Photo in the parking lot outdoors. It's a fun show, www.photofair.com for more information on that. And that's all I've got today, so we will see you in the next video, or perhaps at the next PhotoFair show.